Continue cell growth and division. Try to put our model to test. Try to do something meaningful and see if there's anything wrong with it, how we can get it better. And then learn a few tricks like tracking fields in the simulation, seeing scalars assigned to each cell as fields, and start diffusion in CompuCell 3D. Briefly in the future, we will study tumor, a vascular tumor. So we will need diffused fields for modeling oxygen, nutrients, and waste in tumors. So last time, James covered Steppables, how Steppables are implemented in CompuCell. For example, the start function, step function, and finish function, how it's implemented in CompuCell. Also, this is important, how you get code snippets from Twedit drop-down menus. If you are in XML, you use the CC3D menu to get codes, easy, and examples, and CC3D Python menu for the Python files. Also, we learned how to add steppables, how to access cell objects, attributes like cell volume. There are a few interesting ones, easy ones. For example, if you type cell.volume, you are taking the current volume of the cell. Cell.target volume, you can both get the value and reassign the value. So for example, for cell growth, you take you do cell.target volume plus equals something, you are basically growing the cell in size. Cell.pressure to access information about how much the cell is being actually it's how much the volume is different from the target. So you get a positive pressure if the volume is above the target, or a negative pressure if the volume is below the target. And you can access by doing cell.pressure instead of calculating it. Calculating is not difficult, but it's more convenient. We also learned how to loop over cell lists. There are two important cell lists in CompuCell. The first one is the cell list, which is self.cell_list. And there is a second one, which is the cell list by type. So if you have multiple types on your simulation and you just want to look at one specific type of cell, you do self.cell list by type, give the type name, and you will scan all the cells of a certain type. We learned how to specify some cell attributes in Python instead of XML. And in Python, you have more freedom to manipulate those attributes the way you want. You can tailor these attributes. So we use that for cell growth and cell division. We learn how to do mitosis. We learn about the mitosis steppables. It's a very particular steppables with its own methods hidden. And we learn how to plot stuff. How to do like matplotlib like plots, but not using matplotlib. And from last time, we started the exercise about plotting. If you want to continue doing exercise about plotting, if you love plotting, you can do this exercise here and this exercise. All right? There are more exercises on plotting that you can do. I will leave these as optional for you. And I will jump to my slides. So my slides are a bit different from James' slides. So this is James' original presentation, which is extremely complete. But for this lecture, as I am lecturing, I wanted to build my own slide deck because it fits more my personal my personal style. So I will jump to my slides. Where are they? Okay, here. So what we're going to do today is to put the model we developed last classes about cell growth. We'll try to do something more fun and see if we can get to something natural looking. And from experiments like this picture here, these are epithelial cells. After grown in a constrained environment, they reach confluence and they stop growing. All right. And you can see that they are not all of them the same size, but it's more or less homogeneous, homogeneously distributed, the cell volumes. So I want you to take that simulation of cell growth, the simulation we built, and do this. You build a tube, a narrow 2D lattice, about 40 by 400, and start with a few cells in the bottom, or in the left or in the right, depending on the dimensions of your tube, and let the cells grow there. This is very simple exercise, and before you run, I want you to think what to expect from such simulation. What is the behavior? How will the cells behave as they grow and fill the space? And what do you expect will happen in the steady state? So while we do this, I will keep an eye on the chat because I think people will engage in the class through the chat, not here in my PC. And please go ahead and tell me, what do you expect to see in the steady state? So we have Jonathan, Alex, Emma, and Santu. Every time you build a simulation, you have to set boundary conditions because cells will likely interact with the border. So you have to think about proper boundary conditions for a simulation. And in this case, we have a tube. So it is not isotropic in the sense that left and right is different from top to bottom, right? So are you going to use the same boundary conditions? What are you trying to represent in this simulation to choose a certain boundary condition in the left-right dimension or up-down? Let's start in alphabetical order. Alex, can you tell me what you expect will happen with the cells with the simulation we built last week? What do you expect will happen in the steady state? It's not a super hard system, right? Because you only have cells, they are all identical. They have volume constraint, contact energy, and they are growing, dividing with a very simple rule we set. And they are filling out the space as they grow in this almost one-dimensional lattice. Eventually, they fill out the space. What will happen? What do you expect? I mean, biologically, what do you expect by looking at this picture here? Volumes are more or less distributed homogeneously. cells of bigger and smaller sizes, they are kind of mixed, right? They are mixed. After they equilibrate, they stop moving and dividing as expected, right? Will the simulation accomplish the same behavior? So build this tube and run. Let's see what happens. And I'll give you guys some time to do it. Tell me when you're done, and I will see who can who can show me what's going on. Emma, what do you expect to happen?
So we're using the same setup as we did in our cell growth and division simulation, right?
Yes.
So I guess I expect them to build up, and that will create a pressure in the area where they initially grow, and then they'll spread out to fill the whole tube.
Mm-hmm. Okay, good. What about after they reach equilibrium? How would the equilibrium look like for you? How do you imagine it to look like?
So this is where I'm not sure about the technical details of the model. It might be here the behavior would depart from something we expect, but I would expect real cells to stop growing. Otherwise, they would have so much growth and built up pressure that they would burst out of the tube. I don't know if this makes sense, but I don't remember what the details are of the previous simulation enough to predict how the simulation will work once it does. I can't remember if there's any pressure to down-regulate the growth. I don't think so.
Okay.
Does that make sense?
It does. Yes, it does. It does make sense. Are you able to run the simulation and see what happens?
No, I'm still trying to set it up.
Okay. You can share your screen and I guide you through it.
Well, it's okay.
I stopped sharing. Sure.
It's more that I have to. Sorry, wrong. Can you draw on there's some. What are the reference points for the box initializer again?
The reference points, what do you mean?
For the box initializer. Like when we say box min and box max,
Uh-huh.
what are we specifying in the coordinates for the box?
Box min x is left.
The bottom left corner and then top right corner.
No, box min x is left. Box max x is right.
Oh, okay.
And correspond the same for y. So y min is bottom, y max is top. Let me see you doing it, Emma.
Okay. I have to. So the width is the width of the individual cells? Or
Yes. Yes. How they start. They'll start as squares.
Okay.
And the width is
Okay, so just the volume. Well, okay, first of all, is there some inconsistency with how I set up the box initializer?
let us do something simpler.
Okay.
Let's x go from 0 to 5.
Okay.
0 to 5, and y from 0 to 5. Yeah, one cell. and then with 5 or 7 doesn't matter.
Okay.
Show me your
Steppables.
Steppables. Yeah, let's
So I haven't edited that yet. What did you recommend for the target volume
25 and then lambda volume of 10.
of 10?
10. Why?
It's just a larger.
What?
That's larger than the first.
Why?
Oh, why should you use 10?
Yeah. Instead
Um,
of 2.
So that should make the volume energy very important, right? There's a lot of pressure to achieve the larger volume. They'll grow faster, is that it?
They definitely not necessarily grow faster, but they will be more. Their current volume will be more strictly close to target volume,
Okay.
and this means your cells have less chance of dying by random fluctuations.
Oh, I see, okay.
You know, if you set 0, lambda volume 0, there's no volume constraint.
Yeah.
So they can fluctuate up and down. If you set for 0.0001, they will still fluctuate a lot. Okay. If you set to 100 or 1,000, they will be 25. 25 always, and they will freeze. They will freeze because they cannot either add a pixel or subtract a pixel, so they will freeze. And if you put something in the middle range, let's say 10, you're not forcing them to be 25 pixels of volume, but you are avoiding they die by random fluctuations. And especially in this fluctuation, in this simulation, cells grow and press each other a lot. They can kill themselves simply by one pressing the other against the wall, against other cell, etc. So setting a lambda volume of 10 or even greater than 10 helps keeping the cells alive, basically. Or you can also increase the volume. You could set 50. The cells will be larger. You have fewer cells in the simulation. There's always a trade-off. You have a smaller n, but you keep your cells alive much better. Now you have you have your mitosis. Let's see. Okay, greater than 50, perfect. Random orientation. And please delete the last like 4 or 5 lines.
The update attributes?
Yes. So what are those lines doing?
When the cell divides, we are designating the type of the daughter cell. So we only have one type.
Yeah, exactly.
So if we don't do anything here, will we automatically assign the daughter cell to be of the same type as the parent?
All attributes will be copied.
Okay.
Yes. If you don't do anything, all attributes will be copied from the parent cell to the child cell.
Okay, so we can just delete the whole update attribute.
No.
Okay, I was gonna say.
No.
So that's
because
that's parent to child.
That self.clone parent to child, yeah. It's doing what we're talking about. Yeah.
Then the growth rate, it'd be 1 per step. So is that? I guess we can try that.
Yeah, that's okay. Yeah, let's try it. If it's too fast, we can make it smaller.
So did we need to decide anything about the contact energies?
Not really. I mean, the contact energy in this context is doing what?
It's
Let Alex answer that. Alex, come on.
you want to run this? No.
One crash. Your crash?
Wait, do you want to just sit here and listen to this?
Let's see. Yeah, okay. You can sit her. Yeah, that's a good one. Yeah, instead of getting lost over and over. Let's see.
Well, I don't know if you've been like missing out in the class because you haven't been able to get Jordan because it's all.
What is the role of contact
I don't know.
energy in this simulation, Alex? What is it doing?
Which one?
The growth. I got the first.
Oh, this is, yeah, so this one.
Yeah, I didn't know.
Okay, so now all we're doing is basically adapting, we're making a simulation with the same specs as this one, but the only difference is this one is going to happen in a tube.
So it's like,
See,
oh, it's like
so it's like 40 wide and then
Direct.
400 long, yeah,
okay.
right. And then I didn't set any flux, so there's no wraparound in any of the dimensions.
Okay.
Yeah, so we can just run this, I think.
Max.
Watch, it's gonna completely crash now that I'm sharing screen.
Good answer, Alex. And it's good. It's good to get these answers because we can identify exactly what you didn't understand about contact energy. So it's not that there is like two cells here, and then you adjust the contact energies and they come together or go apart. That's not what contact energy is doing. What contact energy does is setting the affinity of them. So if you have a high affinity between two cells, they tend to stick to each other. But if they are apart, they don't know about each other, they don't do anything. It's not like, there's a high affinity between the two cells, they will come together. No, they don't. Okay? So it's not a force bringing cells together. It's really like a stick. Either they stick or they don't stick, you know? But in order to make something stick, you have to have them come together in the first place. And this contact energy does not do that. So let me help you understanding what's going on. What specifically contact energy is doing. So I will share my screen.
Yeah, okay.
And
Yeah, okay, that's good. Look at them go.
oh, there is a whiteboard. I can.
Look, zoom.
There's a whiteboard here.
Wow. Okay.
Do you see the whiteboard, Alex?
Oh no, oh no. Wait, they're compressing each other. Oh no, they're all gonna die.
Yeah, okay.
Here, let's-
So let's say you have a cell of volume 9, okay? So a target of volume 9. So this cell I just drawn here, it has its target volume. The volume is the target volume, is perfect, minimal energy.
Okay, so
Let's say we don't have contact energy with medium, is 0. In this case, this cell is equivalent
yeah,
to this cell here.
they'll grow so much that like each next step, some will just.
Why are they equivalent? They have the same volume and the contact energy doesn't matter here. We don't have contact energy, so these cells are equivalent. When we have contact energy between our cell and medium, remember, contact energy sums all interfaces between our cell and the medium. So in this case, we have 2 interfaces here, and in this case, we have 4 more interfaces than before. So if we have contact energy, this is not equivalent anymore.
I think I have to.
And if you have a positive contact energy, this one has a lower energy state than this one. This one is in a higher energy state.
Yeah.
So if we add a positive contact energy,
I think I did it in here.
this state here is being favored.
Yeah, here it is.
Okay, so contact energy in our simulation is making cells cohesive, round, okay,
So I'll just
compact objects instead of spread out objects like one pixel here or other pixel there. All right, so this is what contact energy is doing.
I have to make a start here.
Got it?
Wait, was it in it? Yeah, I didn't have to start.
Nice.
I don't remember what.
Let's go back to our shared content. Emma,
Yes.
share again.
Wait, I'm trying to make a graph.
A graph?
Yeah.
No, a graph. Why?
Because I want to see the
Like the
equilibriums. Okay, fine, we can share the two.
Yeah.
You'll see that.
Yes.
Look at it go. It's so fun.
Oh. Oh.
It's so pixelated.
Isn't it? Ooh.
Yeah. But we were trying to see, so we were talking about how like eventually there will be so many cells that the contact between them puts like a pressure for them to be smaller and smaller. And
Oh.
eventually they'll be pushed into such a small space that they fade out of existence. but then more will be produced in the division to replace them. So like the population number will eventually stabilize. Does that make sense? Am I?
Does. But why is that happening?
So in a way, there's a pressure being exerted by the process of growth, but then there's also a counter pressure being exerted by like the contact with the other cells and with the medium, I think.
There's no medium anymore in this stage.
Oh, so the ends, okay, the ends aren't medium. Yeah, I guess that just means the world is 40 by 400 and there's nothing outside of this.
Yeah.
Okay, but so there is basically pressure with like between the individual cells.
Yes.
Yeah.
And the boundaries, right? You have boundaries.
Yeah.
So either if you set no flux boundary, which you did,
Yeah.
I think you did,
I did.
or even if you set periodic boundary,
Well,
in which case a cell collided with another cell, and it's an infinite space, but it's still constrained. In both cases, you have pressure between from cell to cell. They are restricting themselves in space, even if your space is infinite or not. Doesn't matter. Okay. So you're saying that pressure is building up even after filling out everything. Why?
They're still growing.
They're still growing.
Every time step they grow more, even if
they grow more.
During the room. So they just start pushing at each other.
Yeah, perfect. So some cells by accident have a higher target volume than others. They will gain, they will win.
I thought all of them had the same target volume.
But some cells are created later than others.
Oh, right. But they have different actual volumes at different
Yes, exactly. Perfect. Yeah, you guys are getting where I want to be at. So some cells have a huge target volume. All cells have like huge target volume, haven't they? And then some cells have a larger than others. They will win, they will kill the neighbor, and they will be created again, so on and so forth, right? So does this look natural for you biologically?
Realize that the target volume is set to 25 for the cells, but they're supposed to get to 50 to divide. That doesn't.
When the current volume gets to 50, they divide.
Right. Okay.
And when they divide, target volume is divided by 2. So if they got to 50 volume, but their target volume was actually 100, the daughter cells will be 50 target volume, each of them. Because you can have a cell with 1,000 target volume, but 25 volume.
Right. Wait. I don't know. Do you see why I'm confused? Maybe I'm not able to see it. I thought that target volume was like a value used to compute the constraint energy, and the volume itself is the parameter in the cell. So I expect that the volume will decrease when the cell divides, but the target volume will be inherited. Does that make sense?
The target volume will be inherited, yes.
But the actual volume will have.
But we do divide the target volume by 2 if you look at the code in the mitosis Steppables. Yeah. So go to your Steppables.
Yeah.
Yes, perfect. We are actively dividing the target volume by 2.
So that means these cells are actually supposed to have smaller and smaller target volumes.
Yes.
So that means they're going to divide sooner than their parent cells divided.
Yes.
Okay. So that's like super fast proliferation that gets faster and faster.
Yeah, weird. And it's still happening, although we reached supposedly reached the steady state conformal. What is the term? I just forgot. Confluence. Even after confluence, this is still happening.
Why is it called confluence?
I don't know.
Wait, so yeah, I'm not even sure what that is.
Confluence. That's a good question. I can confluence.
They're all doing something together? I don't know.
Yeah, they fill out everything.
Okay.
Confluence, junction of 2 rivers. That's a definition.
Like
It's like coming together.
Was it flow?
It's like coming together, I think. I don't know what it's called. Or process of merging. Yeah, it's not the same meaning, exactly the same meaning, but yeah, it's called confluence. Confluence. All right, so does it look biologically realistic for you guys?
Are you a bio person? Does it look realistic? No.
No.
What would happen if this were
No,
real
it
to us?
doesn't.
It would just all die.
They'd all die.
Yeah, it's like when it reaches, it would just freeze it down. And after like, it's like, cause like every time they divide it, it would just squish the other cells into like another ungrowable like status. And then afterwards it just died. And then when like some alien comes started to die, everything dies.
Oh my gosh.
That's what I like experimented.
What do you think would be realistic biologically?
I think like at the end everything will die. That's
Why?
because like when the cell it's like they're growing in like it's like impacting other cells to live in this situation. So it's like they couldn't live in until like a certain standard, but until that's their standard, everything will die before that thing.
Okay, but I've shown, and I will show my slides, and we have a picture of confluence here. So they don't actually die; they can reach confluence and live harmoniously. That's the case of our epithelium. Our epithelium, when you cut yourself, don't do that. Okay. When you cut yourself, don't do that. They grow, divide, and reach confluence and stop and live harmoniously. All right. We want to achieve that type of behavior with our simulation. Otherwise, we take CompuCell 3D and throw on the trash, right? So we want to fix that. How do we do it? Okay. So you already identified faster than I thought. You already identified what is going wrong with the simulation, what is wrong. So let's fix it. But before we fix it, because I forgot there is a beautiful slide here.
Oh.
We can actually print cell volume, cell pressure, cell target volume, so on and so forth, as fields in our lattice. So this is what you're going to do. Alex, share your screen to us, and I will modify your simulation to include volume, cell volume as a field. So let me stop my share. And you share your screen, your code, and we will make it work. We will implement your code. Well, there's something wrong with the simulation to begin. So yeah, let's fix everything. Come on, let's go. So AAA.xml, that's Alex simulation. So 40 by 400, that's perfect. One cell, go to the bottom. Let's see. 0 to 40, 0 to 5, that looks okay. 5 width, go to Steppables. Oh, before, show me your volume and volume plugin. Let's see if you have a volume plugin in XML.
I guess I need to download those slides to see what.
Looks like you have no volume plugin. Add a volume plugin. So yeah, click outside perfect XML plugins. Volume. So yeah, there you go. Delete what is inside because you want to specify in Python. Nice. Now go to aaa-steppables.py. Perfect. Okay, looks good. Go to the bottom. Let's see if you deleted those. Yeah, okay, nice. So now you will go make a start function. You can do that in the other Steppables. That's better. So add a start. Okay, in the constraint initializer. Perfect. All right. And here you will import the code snippet for tracking fields. So CC3D and extra fields extra fields, and then scalar field cell level in start, init, create, init. Yeah, that's, yeah, perfect. So this should be in the init function. So forget what I said. This goes to in the init function, and take the opportunity and bring that to the growth steppables below in line 25, because we already have a step function there. So we don't need to add a step function in
So we're gonna.
constraint initialize.
Yeah.
Growth step.
Perfect. Now give it a name like volume in these quotes. Yeah.
Does it have to be in caps?
No. It does. Yeah. And then in the step function inside the for loop, import the rest. So go, yes, CC3D Python, extra fields. And the step one, scalar field cell level step, the first, clear, yeah. Or
Clear.
example, could be the example one,
Wait, we don't
imports
have to
everything.
clear it, right?
So this is the clear function. You put that before the for loop, outside, so like line 27. And you have to give the name of the field. So
Oh, you mean like.
no. So instead of scalar,
Then it would clear every single step.
it's scalar field, it's volume, everything, scalar CL field, all of these, it should be. Yeah, I'll open my simulation to
Every
make
time
sure.
there's a step, there's like a while, like time is the required number once it covers steps. And then every time you do a step, you call this. So if you write clear, it clears every single Monte Carlos.
Yeah.
Definitely. But in
All right.
here, I think what it does is like it gets.
You also
all
need
the cell
in
divided simulation,
the,
and then you can like add the volume to each of the cell to the growth, and then you can write basically.
you also need this
Um,
line
volume
in the
to
init.
cell.
Question.
Go ahead.
So we clear it before the for loop, but doesn't that clear all the data before?
Yes, it does, but that's what you want. You want to replace everything by the new values. Every step, you have new
Oh.
values for volume. You want to replace all of them.
Oh, we're not tracking it throughout the whole simulation. We're
No.
just tracking it in the moment.
Oh,
Yes.
Okay.
Yeah, I guess the word is misleading.
Yeah, it is.
Well, it's like I just imagine, we're like making a list of the present volumes and we're going to append that list to like a list of the volumes throughout the whole simulation, but actually we don't care about the history.
Yeah, we don't care. Not yet.
So that's fine. We put in the clear.
Yeah, so you have to add that line. And in line 28, you have field that should be self.field, because this is your field object now, self.field, not field. Yeah, self.field. And actually, yeah, so in this case, I think you just do. Let me see in my simulation, the clear one. Yeah, you don't need that, all that stuff. You can just do the self.field.clear. Yes. In line 28 instead of, yeah, the entire line 28. Yeah. And then inside the for, I mean, we already know how to take code snippets from, I did all of this taking code snippets from Twedit. So inside the for loop, you can add this line. So our cell field, the components are cell, the object cell. And for each cell, we assign the value of its volume. And that's our field. You can save it and run. Let's see what we got. The expand is, let's see what's going on.
Thank you.
Go to the bottom. Steppables.
Oh, no.
So. Okay, go to your Steppables, yeah. So, it has to be exactly the same string. So in line 25, you have volume with uppercase V. In line 26, you have to have volume with uppercase V.
Wait,
No.
No,
This
wait.
is the attribute. In line
ours?
26, volume with capital, yeah.
Yeah, I don't think it's gonna work because we have
Save
all
and run.
lowercase each time and we got the same error, I think.
Really?
Wait, what was the error you got? We also got an error, but I actually didn't check whether it was the same. Ours is attribute error, extra field adapter object has no attribute scalar CL field. Is it? It's in red. Can you scroll up, Alex? Oh, no, we don't have the same.
Yeah, it should be.
So actually,
Good.
but when you fix it, you'll get a different error.
Wait,
Whoa!
It's working. Okay, so now, let me see if I can, no, there's no annotation. So in your graphics window, there is a cell field drop-down menu. Select, yeah, click that. And volume, perfect. Yeah, it's working.
Okay, can I see the code again?
you need help.
I think there was something we didn't edit when we got.
Let me see.
It's this scalar CL field, but I don't know what goes here.
Yeah, so when you clear, the clear acts on the object, so you don't need any of this.
Oh,
Also, just clear.
oh, okay, so you don't even have to assign, that's good.
Mhm.
Okay.
Yeah, should be.
I know.
Oh, yeah, there they are.
And then select instead of cell field. Oh. There we go.
Like
Play.
now it's. Oh, it automatically.
There we go.
It's pretty fun.
Yeah. Yes. Congratulations to everybody. Let me check with the others.
That's true.
So,
I always go first class.
Santo and Santo disappeared. When I said, let me check with everybody, Santo vaporized. Jonathan, how are you doing, man?
I'm doing okay.
Trying
to follow
I'm
along.
sorry, Jonathan, we can't hear you. There is some problem with the audio. We can't hear you
Oh.
half the times in the chat. I'm so sorry. There's something wrong here.
I wonder if we can figure out how to change the color scheme. Oh my god. I'll send them back up.
Doing okay. Okay, fine. All right.
Doing okay.
Doing okay. So yeah, this is, oh, let me show. I'll share my screen back again.
Do you have any idea?
No, I think it should be like,
Where is it? Here.
but it's like a doing conversion.
Am I sharing my screen?
Yeah. Maybe it's.
All right.
there.
So this is the full code in case you want to check. And
Field maybe not.
in the original James slide, there's more information about tracking fields.
I don't think you actually.
And
Or you can-
also what you can do, let me run my simulation and show you something. There's my simulation is full of spoilers.
Oh, cool.
Let me
Oh,
pause this.
Are we gonna see it stabilize? The volume?
Eventually,
Sorry.
today, yes, eventually we will. You can go here, tools, configuration. And in the field, you can see that my minimum field value is fixed at 0. As you can see here, it's fixed at 0 in the bottom. And I unfixed the maximum value. So it can fluctuate to whatever value is the maximum cell volume available in the simulation. In this case, it's 51. And it automatically assigns this blue to red rainbow color scale. And I'm not sure, I don't know if you can change the colors.
So the commission just stick to that.
Yeah, that would work.
X's, no. I think you cannot choose another palette.
That by story instead of volume multiplied by.
Yeah.
Cheated.
So fix the simulation. That's the challenge now. Fix it.
That's a broken. Like how, like what,
Is it achieving something biologically realistic?
No.
he
No.
was saying they should all die.
Yeah, but he's saying that you should.
What we want? We want a beautiful epithelium. That's what we want.
We want it to be organized and like not like they all get to the same size.
Yeah, more or less the same size, not exactly the same size,
Okay.
but homogeneous. That's what we want.
Okay.
So modify, make the model better. That's what we want, okay? So I'll give you 1 minute and a half. No, I'm joking. I'm joking. I'm joking. I'm joking.
That's very gracious.
So, okay. So,
I don't know what these scary scissors do. I hope I didn't actually cut anything, but I think I did.
what did you do?
So cell growth and division is the other one. Tube growth is. No. All right.
So the problem is that you stop the cells from growing too fast because like it's growing at like speed faster than fast.
Okay, so the first thing we can try is just increase the volume by a smaller number. Right? Okay, let's see what happens when we do that. Let's increase it by. So it will grow 4 times more slowly.
But it's still growing infinite.
Yeah,
Right?
but if we also change the contact energies. Okay, but let's see what happens when we just change this first.
I was thinking like if we can set it like maximum of like how like till when.
So I guess that would be by the volume energy.
Yeah.
If
It's like
we
when
set
you
the
reach.
end of the lambda.
Yeah.
So we could make it so that they divide at a volume that's lower than the target volume,
Yeah.
but once they've like filled the whole space. Well, wait, no, but if they're dividing at a volume that's lower than the target volume, then they're never gonna just get to the target volume. They're always gonna divide
If it's near, it should be stopped.
near the target volume.
Yeah.
Okay, now it's just growing really slowly. I think it's the same thing, but more slowly.
Yeah.
Although I'll say it is more homogeneous. It does look like that. Okay,
I mean,
maybe it's just slower. So
yeah, it's slow. Yeah.
It's the same shit but slower.
Yeah,
Yeah.
basically. That's what we did.
Yeah.
So it is what it is.
Okay, good.
Okay, let's just change this back to 1. Let's change the contact energies. In the XML. Let's make them really big. Cell will be like.
Okay.
I don't even know. They spread out more.
Mm.
You might even have to make it bigger.
But, okay. But it's only spread out like in the front. So
Yeah.
it's like afterward, it's just.
Okay, I have a feeling it looks pretty stable. So if we just increase the contact energy even more, then they might be more stable.
Give it a try.
I don't know, it looks like there's less variation to me, but you can veto that if you think there's just as much, but it's just.
It's like, I don't know, because like when it's like, it has like a pattern, like it just gets smaller in some ways,
Yeah.
then just goes down. Like 80% of it's like similar.
Okay.
And people think that, so it's which is like everything same shape.
Yeah, so I guess we need to just make the growth stop at a certain point.
Yeah, I was thinking of that, but then I don't think that works in a real world, if I sell to stop, they would just like,
Well, but don't they mutually regulate each other's weight?
yeah, but they still die and grow in the same time.
Okay,
If that's you wanted.
but
the same.
he doesn't want them to die.
Yeah. So it's like, oh, maybe the growth and the die is like in the same, the speed or like with the same speed, and it will just reach like when the cell die, it grow more.
Yeah.
But
So you
it
can't
also
tell.
like max out the capacity.
What do you mean by that?
It's like, I feel like in order to reach that, that rate and the growth rate should be the same.
Yeah. So, yeah, the number.
Because like it doesn't overflow.
Yeah,
Because like when it no,
I mean, the biological cells?
yeah,
No, they don't overflow.
yeah. So it should reach like similar rates in order to like grow similar.
They don't necessarily need to grow with the same exact rate to reach confluence, and what you need is to, so what is the problem? The problem is that they don't stop growing, right?
Yeah.
yeah,
So once they grow to a certain point, they should stop growing, right? There should be a limit. I mean, each step we are adding 0.1 or 1 target volume. It should stop some eventually, right?
So it's okay. So when it reach a target value at some point, it should stop.
Something like that. For example, after all cells have target volume of 50, why should we keep increasing the volume, the target volume?
Well,
It's 50 already.
so is it possible to make the growth stop after a certain volume?
Isn't it?
Isn't it great?
I mean,
I don't know what's allowed.
everything is allowed. You're in Python.
Um,
You can hack someone's computer in Python.
If cell.volume is less than 15. Okay. We should actually do less than 49 because then we will only get to 49, because otherwise then once they get to 50 they'll develop. I don't know if that makes sense, but then
Yeah, no, that makes sense.
then I'm thinking none of the cells are ever going to divide, but let's see. Yeah, let's see them not divided. Yeah, that sucker is sitting in the corner, not dividing.
Because it's
Hanging out.
49.
Yeah, it only gets to 49 and growth stops. Okay, so we need to figure out something else to do.
Alex, could you figure out how to?
Is it possible to like programming in? Yeah, so can we program in like if this cell has this contact energy, don't divide it? I
Yeah.
feel like that's cheating. It feels so bad.
Jonathan, could you
It's
solve the
not
problem?
even realistic. But I mean, yeah.
Oh my. Here, they're still gonna divide, it's not the same thing. Okay, let's look in the manual what the cell properties are. I don't even know how we can access that.
What is the idea?
We're thinking to basically cheat by saying if the cell's contribution to the contact energy is this, then don't divide.
Yeah, wow. Stop.
Is that just too cheap for this exercise?
No, I mean, a fix is a fix. We are engineering. We're
Okay.
engineers, okay?
Um,
But it should be super simple. Let me tell you a solution. You do this. You assign a global variable called max vol equals 50. Okay. Then you only increase this if target volume is lower than max volume.
we tried that. It didn't, they didn't grow at all.
It just stopped at 4.
Screen share.
Like they grew up to have volume.
Like,
I don't
Around
believe you.
that.
I don't
Yeah,
believe you.
so we did,
Screen share.
we tried. Let me add the thing again, because I deleted. If cell.volume is less than 49. Yeah, so they never divided, but if we do less than 50, okay.
But you forgot an important step. Screen share. Poor Alex. Alex wants to see.
Oh,
No.
okay. I thought you meant share the screen with you.
No, with the class, those guys over there.
Let me make
Okay.
this bigger.
Yes, share the entire screen. You're sharing the
Oh,
useless
thanks.
Compicel window. Yeah.
Who is saying, okay, I don't want to dox myself. Okay. That's what it looks like at the
Okay.
beginning.
Let's go to the XML and reset this contact energy. You're doing mess. It's a mess. I want in normal contact energy.
Okay.
10. Okay. 10.
Okay,
Okay, like normal people. Now go to Steppables and define a global variable. Yeah, we don't need a global variable. Yeah, if cell.target volume, not volume. If cell.target volume is lower than 50, it doesn't grow anymore. And let's run it. Let's see.
okay, I'm starting to understand target volume is complicated. That's what I'm learning. I don't know.
Good news. Good
Yeah.
news. Okay. Let's see.
It already looks like it's gonna work. Yeah, I can,
It already looks it's going to work,
Okay.
right? It's super simple, isn't it? So now you see what's going on. These cells in the bottom, they are under higher pressure, and although their target volume is already 50, they can't grow because they are being pushed by neighboring cells.
yeah.
And only the cells in the boundary, in the border with medium, are the cells that have enough space to grow. And this way you can fill out the space, reach confluence
Wait,
very cheaply, isn't it? Very cheap. And show us the field, the volume field, to see how it is distributed.
it's uniform.
Uniform. It's not exactly what we want, because this is like super hard coded. We're imposing 50 volume. This is not natural. If you look if you look at the biological solution, which is right here, you can see that cells have varying sizes.
Well,
So
we could use a normal distribution around it.
yeah, we can do that randomized.
I can see what my field do, but
let's
it's
force
really
our way.
not.
So
Yeah,
the wise solution is using pressure.
Yeah.
Cell dot pressure.
Like by measuring each sector of pressure. Cause like
Wait a second. Let me see what do they put on the slides? I forgot.
cause like I understand that. Cause like the top when it's growing, the pressure will be lower, but like and the bottom will be higher.
Yes.
So
that they
it
did.
will
so
just
shouldn't
grow.
there like waves of, like there should be fluctuations in pressure all through the,
I think the bottom will be the same, right? Cause like the pressure is always the same at the bottom, and then it will just get less in the top.
Maybe, yeah, maybe. That's a reasonable idea.
And then afterwards it would, but it would just come to the same after a period of time. Cause like the pressure would just be the same if the cell's growing back all the way.
Let's try.
can
Let's
we
try.
quickly go over? I think I forgot how the growth worked from last week. So. It's like so the cell has the target volume, and then when we grow the cell, we're not increasing the cell's volume directly, we're just increasing the cell's target volume. So that the simulation can happen to find a bigger configuration.
Yeah.
Okay, yeah, that, for some reason I deleted that.
Okay, and after I adjust the camera, you got out of it.
Where's the camera pointed now?
Now it's. No. Okay.
Okay, I see.
All right.
I don't actually have an expo marker, so if anyone has it, then we can write on the board, but I don't think.
Here.
Oh, okay.
Okay, go ahead.
I don't-
Then now I have to adjust the camera again.
I don't think that this is actually, like, I don't think I have anything useful to say.
Go ahead. Nobody ever drawn on a board in this class, so go ahead and make history.
So this cell has target volume, and then the lambda volume is basically saying how strictly we have to adhere to the target volume.
Yeah.
So then when we want to grow the cell, we just do like we add 1 to the target volume, and then lambda volume stays the same. So all that's happening here is that the simulation is just like playing around with the different possibilities, but it's more likely to accept possibility that makes this cell 1 larger than before. Is that it?
Yes.
Okay.
The algorithm is always the same. You pick a pixel, you pick a neighbor, offer a copy, accept or not depending on the energy. What you are changing here is the energy. By increasing the target volume, you are changing the volume functional squared.
Oh yeah, wait. When I hear the word functional, there's something very particular that comes to my mind. It's a mathematical concept I don't understand very well. You all don't mean that type of function, do you?
This is the functional.
Okay.
So what is a functional?
Yeah, I need to know that. I've been trying to figure that out.
What is so you don't know functional in any context?
I know about what other people have said around me in pure math contexts, but I haven't been able to understand them.
In a pure mathematical context.
Like it's like a function, but it takes other functions as input rather than numbers.
Yes.
Okay.
Yes, exactly.
Yeah.
So
But I guess I want to.
yes. So for example, let me give you a very easy example of a functional. I will write this functional. So for example, a linear fit. Okay, I have a graph here and points. Okay, and I want to do a linear regression. So I want to see what is the best line that like
It minimizes
do
squared errors.
what minimizes what?
The squared errors,
What is the squared errors?
the deviation.
The functional.
So this, okay, here. So what is the domain for the function?
This is the functional. The y is the y of your function.
Huh.
The yi is the y of each point. You sum for all of them, that's your squared errors, your squared deviations, whatever it's called.
Okay. Yeah.
And this is your function. This is the actual stuff you're trying to minimize. And if you look at this, and actually the formula is, it multiplies by a weight.
Mhm.
It multiplies by a weight. Why it multiplies by a weight? Because some points maybe have a different standard deviations,
Mhm.
right? So you can ponder or weight by a constant that can be different for certain points.
So you're
Now-
manually telling the algorithm, okay, neglect this one just a little bit.
Yeah.
Yeah.
Yeah, exactly. You're weighing different points by a certain way.
Mhm.
Okay?
Yeah.
What does this look like?
It looks like the volume constraint, the quadratic.
Exactly. What is I?
The cells or the pixels with the, wait. It should be the cells, right?
Yes. You have n cells in your simulation. I is the index of each cell. Each cell has its own volume, its own target volume, and its own lambda volume.
Okay.
It's the same formula. So a functional is something you try to minimize.
How does that correspond to what mathematicians talk
Ah, that's a good question.
about?
You so functional is a very you can add other terms here, right?
So yeah, this was what I was thinking, but now it's talking, yeah. This is not as bad as I was thinking. So I think this is the stuff that, like, the squibbling about the continuity of functions and stuff like that. Sorry.
Yeah, I mean, you have a. Yeah, I don't know if this is as general as you can find it.
This definition?
Yeah, this one here. I mean, for E is the functional, right? E is the functional.
Yes.
Depends on certain. Yeah, you're
So
you're minimizing. Yeah, you are minimizing something and trying to find what is the function that minimizes something.
Okay.
Yeah. Yeah, you can. Yes, I mean. Okay, this is not the most general, but
Okay.
functional will be used. For example, here in Compusel,
Okay.
the functional is your energy equation. Basically, this is what you try to minimize. In AI, machine learning, the functional
That's the
is
loss.
the loss.
Yeah.
Exactly, the loss function. So on and so forth. I mean, our brain works with functionals. Let's say, do I eat or go to the bathroom? Do I first go to the bathroom or eat? We have like different weights for each decision, and we try to minimize it, minimize a functional that considers all different decisions, right? Does it make sense? I mean, we are. I'm just giving like intuitive examples, not like formal
Sorry, yeah.
definitions, but it's good when you get a little bit more intimate with the terminology.
Oh, so that explains why I was confused about the target volume thing.
I mean, that.
No, not that, the thing we were talking about with the target volume.
So
Now I
let's implement this. So here what we have, the biological way, let's say, of implementing this in Compusel, the simplest way is by. So we don't want to be like so hard coded. So like obligating the cells. Yeah, this is the volume you have to be. No, we have to achieve the distribution by mechanisms. not imposing the result by what we want to achieve, right? Otherwise, we cannot like adjust our simulation to results. It's only we are like repainting the results. We are not like actually understanding what's going on based on mechanisms, right? So you can never understand, for example, if my mechanism is not enough to achieve a certain distribution. You cannot test that because your simulation doesn't allow it. It's not based on mechanisms, it's based on imposing a certain distribution.
Is it a coincidence that that's the derivative of that?
No, it's not.
Okay.
That's actually, so in physics, let me go to the whiteboard then, because that's a perfect question, because I will soon
The pressure
make you a
rate of
question.
change in volume. Are you a physics background person?
No, but I'm learning physics too right now.
You're an undergrad?
Yeah.
In physics, in thermodynamics, the derivative of energy in respect to volume is pressure. If you remember from high school, how do you write the internal energy of a system? Is pressure times volume plus temperature times entropy, etc.
Wait, is that the ideal gas law or is that something else?
Yeah, it has to do with the ideal gas law, yeah.
So
But this is more general than gas law, ideal gas.
I'm thinking of pressure as like a force over a boundary or something. Is that the wrong idea here?
No, it's not.
Okay.
It is right, but I mean, in the context of CompuCell, it's a different interpretation.
Okay.
Okay, it's not exactly the same because the algorithm doesn't fully correspond to reality. Okay, so it's a different interpretation, but the mathematical derivation must match. Otherwise, we are doing bullshit, right?
It's true.
So E depends on V, S, etc. So if you the partial derivative of E, of course, relative to V is P, pressure, right?
Okay.
In CompuCell, our E is lambda V minus V target squared. So what is the pressure? Partial derivative, the 2 falls down to lambda V minus V target.
Yeah.
What is the surface tension of a cell in CompuCell?
Oh, okay. This is the homework from.
That's
Wait, but isn't that you derive that based on the contact energies, right?
No, if you have only surface energy. What is the surface tension?
I don't remember. I only remember how to.
What is the energy? What is the surface energy?
Like the constraint or something?
Yeah, the
It would
energy
be-
functional
Lambda S minus ST squared.
squared. So what is the surface tension?
Is it the same, like the derivative?
Yes, is the
Okay.
derivative.
2 lambda.
2 lambda
Minus.
surface minus surface target, and that's it.
So it's surface tension is the same thing as pressure applied to the surface?
But pressure is force over area.
Yeah.
Surface tension is pressure over a line.
Okay, yeah, that. Yes, okay, I should write these things down, so I actually. read it.
But we want to implement this. And I'm not sure we have time to do everything. So I will implement this and show you how it looks like. All right. So screen share this. Screen share. And yeah, here's the slide. So pressure is this. P is 2 lambda V minus V target. It means that if our cell volume is greater than the target, P is positive. This is something we have to be careful about. When working with physics, we understand a high pressure would be a very cell being squeezed, but if the cell is being squeezed, the volume is below the target, and this is negative. So we actually have to invert the sign of cell pressure if we want to work in the common interpretation. All right, we have to be careful about that. So, first of all, we have to find what is the standard pressure of our cells. It depends on the volume, it depends on the lambda volume, and it also depends on the other functional terms in our system. In this case, we are also implementing contact energy, and the contact energy between cells and between cells in the medium tend to compress the cells. So the pressure will also be affected by the contact energy. So what we want to do is put a single cell surrounded by medium, not growing, not dividing, nothing, and see what is the average pressure of this cell. So this is the P0, okay? If a cell has a pressure of P0 or lower, provided you inverted the sign, all right, to standardize the interpretation here. So if it's P0 or lower, you allow growth and disallow otherwise. There are certain ways you can do this. So this is more histogram stuff. If you love histograms, you can go through it. Okay. There are certain ways you can do it. You can do an if statement. If cell dot pressure less than P0, grow. All right, let's do that. Actually, no, I didn't do that. I used one of these functionals here. So there is a functional form instead of using an if statement, which are, for example, this one that I like the most, the Hill equation, or Michaelis-Menten. This equation, you don't know this equation? No. So
Can you explain what those variables are? Volume, target volume?
Target volume equals target volume plus growth.
Growth rate, okay,
Growth rate, yeah.
okay, and now we're G prime, that's modified growth rate, not the derivative of the growth rate. Because we don't.
Yeah.
Okay, yeah,
Yes.
FP, that's a function of the pressure.
Yes.
Okay, and
Function of
these
the
are just, okay, yeah,
Yeah, you can use whatever these functions.
okay.
So for example,
Oh,
let's take, let me draw this. Let me grab a whiteboard again. Pressure over pressure plus a P0, okay? If pressure is zero, this function has a value 1 over P0. So it starts somewhere. And as P increases, sorry, wait a second. I'm sorry, this is the activation function. It's actually the opposite. So
yeah,
it's P0 over P, the pressure,
okay,
plus P0. Yeah, now it makes sense. What is the graph of this? So if P is 0, if the pressure is 0, this function gives you a certain value, P0, right? It gives 1. Yeah, 1. Sorry. Yes, 1. What happens if P goes to infinity? 0. The function goes to 0. Is that okay for everyone? All right. So limits, if you do the limits of P going to infinity, this goes to 0. When you raise, I think, everything to the power of n, this power of n will make this curve more and more steep like this around P0.
what is,
So the higher is n, the more switch-like the function will be. And then in this case, if you set a very high n, and I think for this purpose I can share my full screen and go to decimals.
oh, yeah.
Yeah, this is in Italian.
You learn Italian?
I'm trying.
I'm also trying to learn Italian. Do you know other people? We can have like a little group.
Yeah.
That's cool.
Yeah, but I'm like not like working on it. I just like put everything in Italian and try to click it. I try to click
I
stuff.
should try to learn Mandarin that way. I would hate my life.
Yeah. So here we have 1 over x plus 1. And 1 to the n is 1. So let's do
Oh,
x
yeah,
to
I
the
see
n.
fraction.
So what happens when we increase the n? We increase the steepness of the function.
Oh,
So let's do to 100 from 0 to 100.
Sorry. I should.
Grafico senza titolo or titolo.
That means graph without title, right?
Yes.
Yes. I'm speaking Italian now. Okay, okay, we'll talk about how we learn Italian.
Yeah. So if we set for a very high n, it's a switch function. And then in this case, if p is less than p0, the cell grow and not otherwise. It's like an if statement. But
Oh,
biology is more flexible.
yeah, flexible.
So you set an n like 5, 6, something like that. I hope that was clear. I will switch now to my slides and my simulation. So what I did in the simulation, and I didn't need to do that actually, but in the simulation, what I did here was basically writing the functional, right? I have here P equals cell dot pressure.
wait, why do we need it to be 1 times?
Because this you can transform in a cell growth or growth, growth rate. But really, the idea is that you can just switch back and forth by doing this. Okay, so this is very convenient. You just put a hashtag in front of the functional and you deactivate the functional to compare, right? So if I do that and I run the simulation, and I also have a histogram here. Beautiful histogram. And
Happens.
Okay, let's undo that then. Okay. All right.
There's like no energy, no cells.
So they're not glowing.
Yeah.
Wait, oh, it should be cell dot target volume is plus equals. I think that's the error.
Yeah.
Wait, can I copy that? Prep
Yes.
to the power of n divided by prep to the power of n plus np fabs. I don't know what any of this means. I can just code my here.
It's
Fabs.
equation, so it doesn't matter.
What is
Fabs is the nickname of someone.
Okay.
Fabs is float absolute value.
Oh, okay.
So because
Oh.
P pressure can be negative. And if P pressure is negative and our exponent n is odd, it yields a negative number.
Is fabs the standard Python?
NP dot fabs.
Oh, np. That's what it.
NP dot fabs.
I was like,
yes.
np is pressure, right? N times p. No. I need to turn off.
It's the non-pressure.
Okay. And I don't think I put pref in. Where do you define pref? Is it a global variable?
Yeah, it is a global variable 40.
Pref
Why?
equals 40. Because
Why?
I didn't define it, so it's not gonna.
But why is 40?
Why is it 40?
Yes.
Let's think.
I explained before.
Okay. That's the.
You
point
take
every
a
time
cell,
I
you take
stop.
the cells, you run a simulation with an isolated in medium alone without anything,
Oh, and you get
It's like
that.
and that's the average, more or less.
Okay.
Okay. So that's the threshold you want the cells to decide whether to divide or not. All right.
And it's not defined.
Oh yeah, so if I run, here's a volume. This is the behavior. So you see, I have a more variability in the volume, and they are mixed. They are kind of homogeneously distributed. I don't have like weird certain regions of high pressure, weird regions of lower pressure. They're homogeneously more or less distributed, mixed. And when they reach confluence, it's a beautiful epithelium, like we wanted, right? Here, oh no. This, all right? And let me show you how it looks when I deactivate. So if I come here and deactivate my functional, come back to the simulation and run again. It's that BS we talked before. All right. And if you see the histogram here, the histogram is giving us some interesting information. I have cells with 0 volume. You see, like 30 cells with 0 volume. What is that? You know? And when I show you the other histogram.
Wait, isn't it between 0 and 10?
What?
cells with 0 and 10 volume?
Yeah. Yeah, but I mean roughly. And when I plot the histogram with pressure controlled growth, my cells are between 20 and 50 volume, which makes sense. That's what we should expect from a normal simulation, normal biologically relevant simulation. And we didn't impose that. That's the cool thing. It's a mechanism. So there is a function, a signal to growth, or a signal that inhibits growth based on the contact of the cell with its environment. And this is actually something you can measure the growth of cells in different constrained environments and adjust those constants, adjust the growth rate, adjust the n, and the exponent. You can find the exponent by fitting the simulation results to experimental results. And then you find something that is meaningful for biology, like the growth rate or the inhibition coefficient or something, all right? Then you're doing science. Otherwise, you're making a movie for your
doesn't know.
Yes, exactly.
I'm telling you, that's what the people in my field do. They say, yeah, we're gonna model this with a normal distribution, page your paper.
Yes, exactly. Yeah. It's done. All right. So to plot the histogram, let me show this quickly for you. Of course, the James slides is complete and it's gonna be in the homework. All right. But it's super simple. Look at this. And I will give you the syntax. I will copy and paste in the chat. So it's the same thing. You go to edit menu here.
Would you mind to just highlight the comment? It's harder for me to read on the phone.
To what?
Could you highlight the leading comment just so I can see where it is, but not highlight the actual text because I can't read? Yeah.
All right.
Thank you. It's easier for me to read this one.
It's the same thing. You come to Python, scientific plots histogram. You can add a histogram. There will be an example for your start function and an example for your step function. And so to plot a single histogram, these are the lines for the start. So I will copy and paste here. So, I mean, you don't need that because you can access using the Python, the Compicell stuff. And if you look here in line 40, I have, so to help Emma, I initialize an empty list. Then I populate the list. All right, populate with cell volumes. and pass this list into this entire code here. This line of code. Yeah, sorry. So you just pass the list volumes, okay? And you set the number of bins and it's done. All right. I'll copy and paste this. And line 48 is just to do that every 50 Monte Carlo steps. All right.
Wait, so that modulo operator, that's gonna be the number from 0 to 49, right?
Huh?
So MCS mod 50 is gonna be a number between 0 and 49, right?
Yes.
Okay, so if not, do we want to do something when that number is not equal to 0? Is that it? Would that
So
be-
think with me.
Yeah.
When is MCS by 50 0? When is this 0?
When the Monte Carlo step is a multiple of 50.
Yeah.
Yeah.
So every 50 Monte Carlo steps, this
Yeah.
number is 0.
Yeah.
If you give it a knot, it's 1. And then
Okay.
you do the state. That's a convenient thing for you to memorize. If not, MCS
Okay.
percent something. It's every something. That's a convenient thing to memorize, and then I just don't think I just type.
Okay, so I always do MCS mod 50 equal to 1. If that is equal to 1, then
Yeah,
or
it could be,
is
yeah.
equal to 0,
Yes,
right? Yeah.
yes, exactly. Same,
But okay.
yes. All right.
Wait, I'm still,
What?
my intuition is that that will actually print 49 times out of 50.
That will happen if you do this.
Okay. Yeah. Oh, if it's not 0, I see.
Yes.
So anything other than 0 will just be course to 1 for evaluation as logical.
Yes.
Okay.
Exactly. Everything not 0 is true.
This one, okay.
Okay. Let's go back to the presentation. So we implemented this. And I gave you the snippets, and this is quite simple and super cheap, right? This is extremely cheap for a mechanism. Then histograms, I recommend you go through these. There are lots of detail, but it all boils down to the 4 lines I copy and paste in the chat. Okay, so there's no mystery here, nothing special. But go ahead and take a look at the slides if you really love histograms.
Will the slides be posted?
No, sorry, they will. And I am appending, so my slides are appended to the end of the presentation. For the previous slides are James' original slides, okay? So we learned here how to regulate cell growth by pressure, contact inhibited growth. But there are multiple ways you can implement inhibition of growth in different kinds of simulations, different contexts. For example, depending on the amount of nutrient. Let's say you have a tumor grown and the tumor depends on oxygen to grow. Or it inversely depends on the concentration of lactic acid to grow, and so on and so forth. Growth factors, right? So let's say you're modeling tissue engineering and you want to grow a cell population in a scaffold, and you put growth factors in the scaffold to help the cells populate the scaffold. So growth factors play a role in that, all right? Contact with other cells or substrate. Some cells only grow when they are in contact with other cells, otherwise they migrate or other behaviors.
Is that like the mesenchymal cells?
Yes. Or yeah, you have the epithelial mesenchymal transition, so and the inverse. Presence of toxins, etc. Metabolism. If you inhibit cell metabolism, it's going to be different, I guarantee. Now we will start with fields. So hopefully we'll cover everything from scalar fields to quantum field theory today. No, I'm joking.
That's what I want.
Yeah, that's what we want. So what is a field? For the purpose of biology. Okay, let's not be too mathematical here. Field is something that is defined in space and time. Okay. It could be cell volume. Cell volume can be a field. For each point in space, you have a cell with a volume. For each point in time, you have a volume, different volume in time. Okay. It can be a scalar. It can be a vector. So, for example, cell polarization. Cell polarization is a vector.
Can you remind me of what that is?
Polarization.
Polarization.
For example, my polarization is this and this, for example.
Does your eyes face forward?
Yes,
Okay.
and my head faces up.
Okay.
Okay, so
But
you can have a really symmetrical cell. Let's say yeah, or for example, during cell division, eventually you have a polarization axis because you have to split the cell in two, right? And it's asymmetrical. Or for example, cell migration. Cell migration is fundamentally a polarized system because the cell has to move in a certain direction.
Yeah.
If it's just like wiggling around, it's not polarized and it's diffusing, right?
Okay.
That's by the way, that's how I dance in the night. So that's an example of a vector field. Okay, a gradient of a scalar field is also a vector field. And we could also have like tensorial fields, tensor fields. In the case of biology, what would be an interesting tensor field? Good question. Yeah. I don't even know.
Would it be like? It's too abstract, but
Go.
so if a cell is moving through like a gradient, like a diffusion gradient, and there's like chemotaxis going on.
Okay.
If the cell is changing how it responds to the values of the gradient at different points in time, is that an example?
No. But it's nice try. A good one would be, for example, what is the shape of the cell? Is it more elongated? Is it more spherical? This is described by a tensor.
Why is that described by a tensor?
It's the inertia tensor. If you take something and you rotate this, it has some inertia. If you rotate this, it's another inertia. Right? So the inertia tensor gives you the weight of the object in each direction, like how elongated it is in each direction. Or it could be, for example, let me think of another tensor interesting. Stress tensor. Stress, strain. Because when you apply stress to something, for example, I apply stress like this, but what happens? It also shrinks in this direction. You cannot describe this as a vector. You have to describe as a tensor because you do this in one direction and affects the others. And this happens to cells. In cells, if you stretch a cell like this, it shrinks in the other direction. So a stress tensor could be a field. We will have cells spread out in the lattice. Each cell has a stress, a tensor stress.
Yeah, I don't think maybe my assumptions about tensors are going to be too technical. What do you mean? What do physicists mean when they say tensor? Explain like I'm fine.
I don't know any other definition other than a tensor is something that transforms as a tensor. And then there is a rule for that.
Okay.
That you memorize. Is basically like the derivative of each component in one coordinate system relative to the other. So if you change the coordinate system, the tensor changes correspondingly according to the derivatives of each component to the other of one coordinate system to the other.
Wow.
Yeah, it obeys transformation rules.
Okay.
Yeah, that's it.
Okay.
But it's not a matrix. Matrix is more general.
Wait, I thought tensors were generalizations of matrices.
No. It's the opposite.
No,
Tensors are very
Tensors
special,
are-
very
matrices
special
are
matrix.
second rate tensors. And zeroth rate tensors are scalars.
Yes.
But that means that tensor is like more general than matrix if matrix is a special case of tensor. Like
Matrix is more
tensor
general.
rate equals 2.
But you can have a 3D matrix. You can have a 0-dimensional matrix. It's a scalar. You can define that.
Yeah.
It's not
But
a
that's
problem.
also a 0-dimensional tensor, according, well, but,
No, but a 0-dimensional tensor has specific transformation rules.
okay,
Yeah, it is tied to coordinate transformations. Okay, so let me give you a physical example of a tensor, a scalar tensor specifically. And mass is not one of them,
okay,
because if you change your mass, rest mass is a tensor, because even if you change your how faster you are in relative to the person, the rest mass is the same.
okay,
But for example, something that is a scalar but doesn't work like that, it's for example density. Okay, density is a scalar, but if you move fast relative to that system, the density changes because it can dilate. There's the time dilation and length. Exactly.
okay.
Let's
Okay,
go back to bio. So this is an interesting simulation from through Blue and Brown about diffusion. Okay, and this is this could be concentration, this could be temperature, and it's diffusing throughout space by a very specific equation called diffusion equation. Okay, there are many ways of representing fields. You can represent as shapes, curves. You can represent as isosurfaces. For example, here, this is a screenshot from Castel. And I'm sure you have seen these in maps. These are all iso lines, isosurfaces, whatever. So each line corresponds to a certain scalar value, and a continuous line has the same scalar associated. And you can also represent at heat maps, and this specific heat maps is like, I don't know, could be anything. This is an example of a vector field. This is, for example, a velocity field in a fluid. This is used a lot in cell migration too, so it's important. So here are some questions. We kind of addressed all of them. Can you think of scalar fields in biology, concentration of something? Or for example, the volume of cells. Vector field, the gradient of a field, or polarization or velocity. Tensor fields like stress, strain, or inertia tensor. Concentration, we use the letter C, and they represent basically the density of a certain molecule in space. You can normalize that, so it's between 0 and 1. If this molecule saturates, etc. One example is VEGF, and generally in experiments, concentration is given by fluorescence. So you tag the molecule with an antibody, or yeah, that's usually how we do, or radioactive leucine to tag certain proteins, and then by imaging, you can get a sense of how concentrated it is.
I think I remember learning in high school that fluorescence happens when you excite the electrons in something, they jump to like a higher energy level and they go back down and emit a photon.
Yes.
Is that bunk? Like, is that just a lie that people tell if you don't know anything about quantum mechanics?
after the class.
Okay, sorry.
But it is not a lie. It is not a lie. Okay. Is the gradient of a field a field? Yes, it is. Is a vector field, right? I think everyone here should be more or less. Alex, please. I know you are not a mathematician or a physicist. My English is you're from bad to worse. A physicist, yes. And if you're not familiar, if you need explanation about something, please jump in and make my life a hell. General definition of a scalar field. It's generally symbolized, okay, by nabla and nabla, yes. Okay. And the letter of the field. So for example, your field is F, this shape, this beautiful shape is F. Nabla F, the gradient of F is this vector field in the XY plane. All right. And the gradient indicates where your field grows. So if you are sitting in the middle of this field here, all directions grow, your gradient is 0. If you stand, for example, here, you can see that it's pointing in the direction of the growth. When we talk, and this is very often people talk about gradient descent in machine learning, in protein folding, etc. Is what? What is a gradient descent? If you invert this arrow, you are pointing to the minimum. That's how we do a gradient descent. Come on, fast. Here we have a heat map and some questions. Let's see what the questions are. Is the gradient of a concentration field relevant to biology? As it is. Can you think of real situation? Okay. Next, diffusion. So what is diffusion? Diffusion is this natural transition of molecules from the high concentration to the low concentration regions. All right. Does this require energy? What does this require?
But they also have to be moving around.
Yeah.
Because if it's just at a high concentration, but they're sitting there, then nothing's gonna happen.
So what does it need?
Yeah, energy, average temperature. Yeah.
Good. But do they need to collide to each other?
Yes, and push each other around.
No.
No?
No. Look at this simulation. They are not colliding.
Oh, because of the
It's by chance.
probabilistic, yeah.
It's probabilistic. It's fundamentally probabilistic. They don't need to collide. They're not colliding. Merely the fact that there are more particles here and less particles here, the tendency is to equilibrate. So a physicist would say, no, there is a force. There is a force. It's a generalized force called chemical potential.
Yeah.
But no one cares.
Okay.
I think neuroscientists take that seriously. The chemical potential. They say it's
Yeah, but it's not because of this. It's not this reason. No, they take it because of neurons. Yes, they take it seriously. Yes, but they don't call it generalized force.
yeah, they just say, well, there's a force.
Yeah, chemical potential.
Yeah,
Chemical potential.
Yeah, basically. Okay, wait, let me just make sure I can get this into my memory so I don't just forget.
Just give me some 5 seconds of looking. Let's run again.
Okay.
This is the Ehrenfest model. You can solve the equations. It's pretty simple.
Right, and so the thing about this model is there's no term for forces involved with collisions. They just pass through each other.
Yeah.
Okay.
Yeah, but does that mean that every time they diffuse in different rates? Because I guess possibility of like floating from high concentration to low.
Yes, so the rate of particle exchange between the two compartments is proportional to the concentration in each compartment.
Yeah, but it doesn't make sense if there's like a higher concentration in one end and with the high concentration, it would have similar rates. Because like
They have similar, notice that they keep exchanging particles, but they exchange at the same rate.
yeah, but if the
What's
left side is way higher,
Mhm.
it's like higher than this one, it's still the same rate.
No, it will be higher.
But
You have a different rate between from left, right, and right, left.
So I think it's like, okay, if there are more particles in general and they're all moving independently, the probability that any one particle will be in the tunnel is a set number. When you have more particles, you're just multiplying, like you're adding that probability over and over.
oh,
Does
is
that
that
make sense?
Yes.
okay?
So like you're taking a sample with each particle for it being in the tunnel.
Oh, okay.
So you just add them up to get the probability that from this side, there's going to be
Like a
traveler
certain
in the
number
tunnel.
was going to
Yeah.
the other one.
Versus like the other one, there are just fewer particles that could be in the tunnel. So the probability that any one of them will be in the tunnel, or sorry, the probability that you will see particles in the tunnel is lower.
Oh, okay.
There's a cool story. Once I was trying to explain diffusion for people from the countryside of Brazil with poor background in mathematics, and the only way I could explain diffusion was with this example. You have two dogs, one of them full of those insects. What is the name of the insect? The small insect in dogs.
Fleas.
Fleas.
Yeah.
Yes. One dog full of fleas, the other dog with zero fleas. What do you expect will happen?
Yeah,
It's probabilistic.
because the fleas, they're not, like, they don't know where they're going. Well, okay,
Yeah.
like, they do probably in the sense like carbon dioxide, but let's just say the fleas are stupid, they just jump randomly.
Yes, exactly.
But, yeah, I know mosquitoes go up the CO2 gradient, so they actually do react too,
Yeah, they do. Yeah.
yeah.
Let's move on here. So of course, spatial configuration will affect how things diffuse, because things can either get blocked by things they cannot diffuse through, or they can stick to certain things, right? So when you're talking about, let's say in my case, okay, I want to build a simulation of interferon response in cells that are infected by a virus. And then I want to know what is the diffusion rate of interferon in water, okay? And then I grab that value and build my simulation based on that value. But actually what happens is that interferon, they bind to membrane receptors and they stop diffusing. So I might get a very different simulation from reality if I don't consider this.
So would it have to be that you increase your diffusion rate as the simulation goes on, since the concentration will decrease?
What you do is you say that the cell is capturing that molecule. So you subtract from the field. That's what you do usually. If it's subtracts and then it releases, you can do both. You can both subtract and add later. The thing why diffusion is important in biology is that it's a cheap transport. Okay, doesn't require energy. So you can have cell communication, and you can have also distribution of resources like nutrients, gases, toxins. Okay. A situation where diffusion is critical for multicellular systems of survivability is, for example, oxygen in our tissues. Okay. And in development, certain chemical I forgot the name. Some factors, chemical factors, regulate development, and the fact that they can diffuse through cells is important. So on and so forth. For single cell survivability, for example, nutrient fields. If you can sense nutrient fields and if nutrients diffuse and toxins diffuse, you don't accumulate toxins all in your position.
If you do also have collisions between the diffusants, is the rate increased relative to what it would be if they were just doing it probabilistically? Or does the movement cancel out, I guess, and
I would say it's the same. it's definitely not the same when you have volume exclusion. When they occupy space, they occupy a certain space. If they occupy a certain space, then the pressure will be higher, they will spread faster. Okay. Because if they collide, but they are still point-like particles, they are doing this. It's the same as they just cross each other.
Yeah.
And if they do this, who cares? But if they are like big, then yeah, it's different. They're big, but they occupy space. They have higher chance of collision. You know, higher chances. Actually, if they are point-like particles, they never collide.
But that can't be an accurate description of reality, right? Like particles.
So the answer is in gas-like systems, like ideal gas systems, they do exist, and the particles are so tiny they rarely collide. So
is the pressure just from the particles colliding with the container?
oh, by the way, in that simulation we have pressure, right? We have pressure,
Right.
Because they collide with
The walls of the container.
yeah, with the walls. Yes.
Interesting.
But pressure is whether or not your particles are moving. Okay, if they move and they cross regions of space, this is pressure. There's no way around. Okay. Transmembrane diffusion, this is very important. You have, for example, water can cross membranes freely, but for example, ions are ions carry a huge cloud of water molecules around because they are charged particles and they cannot cross the membrane. So they have ion channels or gated channels, gated gates, let's say, yeah, gates that can open or close depending on something, and then you allow diffusion. This is a very cool video that illustrates that diffusion is very unimportant in large scales. So if you see here, it really looks, although it's dye in water, you don't see diffusion taking place. So a bunch of videos you see in the internet where the dye is spreading, it's bullshit. Why? I'm being too.
They put it in really small space and then they film it?
No. In cups.
They
But
shake it.
what is the problem? You didn't wait long enough for advection to stop. You still have the fluid moving and gradients of temperature that makes the fluid move. So you get advection and everything mix, right?
Does the fluid have to be hotter than the surrounding environment to have advection? What causes it?
I think
You just need a temperature gradient in the fluid.
Okay, so when you put in the dye, that is the.
it's like there's temperature change, like difference between the dye and water.
Well, everything. When you drop a dye, it's already perturbing the environment. It's going to cause advection and mix. But here he did a very careful experiment. He put the bottle in an aquarium. He waited many days,
I see.
very still, and then put the dye with a syringe very carefully, closed inside the aquarium, took it off, and then he can even shake it up and down. I didn't show you this. He can shake up and down.
Yeah.
No, this is sideways. Yeah, he can shake up and down because it's sealed and you're doing this, the entire column of fluid is moving together. It doesn't do anything. It only mixes when you cause advection. Doesn't mean that diffusion is not happening. It is happening, but you would have to look with a microscope to see that column of dye to spread. Okay. That's why we have blood vessels. So the diffusion equation, you will not solve the diffusion equation, of course, but it's good to know how it looks like because it will appear. It will show up in papers. Many mathematical models use those. All right. So basically, whenever you see a time derivative equals a Laplacian like this, it means spread. Something spreading out. Okay? Spread out behavior. By the way, the Schrödinger equation is a diffusion equation, but in complex space. So whenever you have a particle, it spreads out. In complex space, but it spreads out. So if you just wait, suddenly you are measuring the particle far further away from where it was, which is cool. And this is what we call a continuous model. What would be an agent-based model of diffusion? The Ehrenfest model, the one we saw before. What are the agents? The particles moving around. Here, this is the continuous model. This is an abstraction. Okay, this is representing the overall behavior of an ensemble of particles moving around. D is the diffusion constant. C is our concentration. And that's it. That cool video again. And as I said, whenever you have diffusion, your field may interact with the boundaries, and you have to set boundary rules, boundary conditions. So first you ask yourself, what happens when my field touches a boundary? So let's think, for example, let's say I fart over here, okay? I fart here, and then the concentration of CH4 reaches this wall. What is gonna happen here?
Bounces this way.
It doesn't cross, it doesn't do anything. Is the wall going to suck up? No. Is it going to help releasing more? No, it's not doing anything. So there is no exchange of fart with the wall. In this case, you use a constant derivative 0.
Oh.
What is derivative? Is rate of exchange. What is 0? Not happening. That's what this wall is doing. What is happening in the door? The door allows, helps us. So in that case, we could set, for example, a constant value 0. There is no fart outside the room. Okay? And in this case, if there is 0 fart outside and some fart inside, there is a flow of fart outside the door, right? Or let's say someone farted outside the door. Then suddenly, or lots of people farting in the corridor. then you set a constant value of 1 outside, and then there is an influx of fart inside. What about periodic? Periodic when you
The derivative is fluctuating?
no.
Okay. Oh, you mean the boundary is periodic?
The boundary, periodic boundary. Yeah. What is periodic boundary?
It's just like a continuous space. So there's
Infinite space.
Yeah.
Periodic space too, right? If you tile this, like this, it's the same picture over and over, right? Periodic is basically something, it crosses the boundary in one end and appears in the other. That's what periodic is. And hopefully, yeah, we have this video. This is periodic boundary conditions in games. Why would you use this in cell environments, in cell simulations? Alex, why would you use that in biological simulations?
You don't want it to just go out.
Where is Alex? Alex, my friend.
Oh, you mean like the
Why?
cell cycle?
Yeah.
But I guess here the periodic actually applies to the space that the cell is, not the cell itself.
Okay.
But remember when we had the cell movement simulation? We had to set it to periodic because otherwise the cell would just move away. Yeah.
Moved out of the.
Is it in part because of the cell size of the real life organism compared to the size? Good. That's it, Alex. Did you get it?
You mean that we want to get more space out of less space, essentially?
Yes.
Okay, yeah.
You're modeling an epithelium, for example. It's a skin, piece of skin.
Yeah.
If you take a 1 millimeter by 1 millimeter piece of skin, it's like millions of cells, but you're actually simulating 1,000.
Yeah.
So if you set a boundary, a rigid boundary, it's a wrong simulation. You set boundary conditions so that this cell interacts with this cell, but that's not realistic. But they are far away from each other. They don't communicate. So it's safe. You are assuming that these cells are not communicating. They are distant enough. And then you do periodic, now they are communicating and they are behaving in a local environment on their own. So you have to assume your simulation is big enough to allow boundary conditions. Okay. Otherwise, for example, the extreme opposite case is, for example, a periodic boundary condition. I stretch my hand here, I grab my own hand over here. Okay, and then I'm interacting with myself. It doesn't make sense. Okay, that's the extreme opposite case. Oh, let me close this. So I have some questions here about periodic boundary conditions. First one, how would you model the boundary condition of oxygen given you are simulating a tumor and your boundary is a blood vessel?
Wait, so we have our little simulation square. We're saying the tumor is inside the square, and we're going to imagine that the borders of the square are representing a blood vessel.
Yeah.
Okay.
And oxygen is our field. How would that boundary condition be?
So wait, we're imagining the tumor bordered on all four sides by blood vessels?
Or just one, whatever. Yeah, one of the boundaries is a blood vessel. If it's a blood vessel, what is the boundary condition of oxygen?
So the oxygen can diffuse out of the blood vessel, right?
Yeah.
Yeah, but the tumor can't interact with itself through the blood vessel.
But I know wait a second.
Okay.
So the boundary condition not for the cells. I mean,
Okay.
the tumor is there inside. It's not like crossing.
Okay.
No, the tumor is sitting there. Okay.
Okay.
Relative to the oxygen field. Okay, in respect to the oxygen.
So the derivative is not zero.
I think oxygen's flowing
Yeah.
into the tumor.
So we're gonna distinguish outward flow from inward flow. One would be positive, one negative. Is that it?
Well, blood vessel higher in oxygen, so
Yeah.
it can flow into the
Flow into
tumor.
the tumor.
Okay. So which one of these? Or another one? Constant equals zero?
Not zero. Wait,
It's not.
can you explain the difference between
Yeah.
constant derivative for the diffusion versus constant value for diffusion? Because I know you had the wall example, but
Yeah, so the example is the wall is constant derivative zero. The outside is constant value zero.
okay.
Okay. Because I'm imagining the corridor is a reservoir of air with 0% of a certain one.
Okay.
But it could be the opposite. I could imagine for example,
Like 10 out there.
yeah,
Yeah.
fixed
that would
10.
be the blood.
That's a
Yeah,
reservoir.
that'll be blood.
I mean, if
So
you simplify it and say that the concentration of oxygen in the blood vessel is constant, we can just say it's constant positive value outside.
yeah.
Okay.
That's your bet?
Yeah.
That's right.
Okay.
Why?
Show.
Why can you safely assume is a constant value?
What?
Will it average to the same value? I mean, the oxygen in the blood vessel, I don't know a lot about.
But you take the oxygen out.
Yeah.
Doesn't it run out of oxygen?
No, because we're breathing.
Yeah.
It's okay.
It's super
But-
fast.
But I actually don't know what the time scale for that is when you breathe. How fast does your blood get?
It's super fast.
Yeah,
It's
it's
the
super
scale
fast.
of your breath. It's the scale of your breath.
It's like it's exchanging so fast that it doesn't really.
It exchanges
Okay.
super fast. And the time scale of tumor is months.
I see, okay.
So it doesn't
Yeah, I
make sense to consider depletion of oxygen.
Okay,
Okay.
so just say it's a constant supply of
Yeah.
on
Yes,
the outside.
exactly. Perfect.
So we're not, can you go back to that tree diagram? Or, yeah. Okay. But there is a flow inward, right?
There will be a flow.
Yeah.
Right, so would it-
When there will not be a flow in that case.
The tumor died or like the blood vessel stops.
Less and less dramatic.
Less dramatic,
oxygen
okay.
concentration in tumor is the same as in blood vessels.
Exactly.
Okay, so I see. So we don't say it's derivative because it's not going to be a continual flow. The flow can be
Yes.
regular, like downward.
Exactly,
Okay.
exactly. So constant derivative above zero, for example, would be like something pumping
Okay,
that field inside.
so that's like, oh, a researcher is continually injecting this fluid into the system. Continually, like we have a machine.
Yes, exactly.
I see.
Or our cell secreting.
Okay, so how would you model, like, the researcher has the machine to inject something into the, let's say it's a petri dish, but it's going to inject and then wait 10 seconds and then inject again, so it's like a periodic injection. Would you just model that by like a derivative, just say average inflow?
In this case, I would model as like Dirac deltas,
Okay.
like in a certain time point,
Oh.
I add 100 to the field at a certain region, and then in the place I add again,
Uh-huh.
and you add a certain value of that concentration at a certain particular position. That's how we'll do. Let's see another example. You have an epithelium.
Like this?
Like like that. You have your epithelium, and there is the outer environment here,
Oh.
air. Okay,
Okay.
and
There's
there is a
temperature.
glucose field in your epithelium, hopefully. I hope, if you're healthy.
Yeah.
How is the outer environment behaving?
It doesn't have anything outside.
Huh?
It doesn't have glucose field outside.
I would hope not, unless we
Yeah.
just like evaporate out our glucose. I mean, at one temperature, does glucose become a gas? Is that even possible? It would just make that.
It is.
Okay.
It is.
So constant zero, I guess,
Constant what?
zero, right?
Constant value?
Constant value outside?
Yeah.
Yeah, cause like, wait,
No, but the concentration of glucose outside is zero.
Yeah. So constant zero, or is that wrong?
But if we model that as our boundary condition, what will happen? We will lose glucose to the air.
I
Does it
thought
make
constant
sense?
zero is like when you have the wall and the fart does not diffuse through the wall.
Constant derivative.
Oh, sorry, wait,
Oh.
can you go back? I'm already forgetting.
So constant derivative.
I need more glucose.
Yeah.
Yeah, okay, so the rate of change is zero. That's.
Yes,
Yeah,
that's
what I want.
that's how it
Okay.
works.
Okay,
Yeah.
constant zero is like, the door is shut and nothing is going out, so outside is,
Constant derivative. So now the door is open, there is a reservoir outside, then constant value.
okay,
Either providing or removing.
versus like the rate of change is just zero, there is no change. Okay.
Yes.
Maybe this time I'll remember it.
A site of tissue where cells communicate via growth factor. And the adjacent sites have the same behavior.
Wait, okay, so here's like blob A and there's blob B and they're touching.
Mhm.
And there are growth factors in blob A and blob B, and they can go through the boundary.
You're modeling only one set of cells, a site.
Oh, okay, and then
Site.
outside we're pretending it's blob B.
The outside we're pretending is the same stuff from inside. We are modeling a piece of it,
oh,
Okay.
a site. We are modeling a small site of a whole piece of tissue, and they all behave the same.
periodic.
Period.
Periodic boundary.
Yeah.
Yeah. Okay.
That's what Alex told us in the
Oh, I
chat.
see. Okay.
All right. You are pretending your simulation is part of a bigger system.
So it's like a donut made of the cells. Like the cells are on the surface of the donut.
Yes.
Yeah,
Of
okay.
the
It's-
torus.
It's like you take you take this napkin and you fold it like this, right? And you stick these ends together.
Oh,
And
yeah,
you
yeah.
imagine you can just bend it in space to make a donut. Yeah.
Yes, and that's it, yes. And then all boundaries communicate.
Yeah.
That's it. There's a cool video showing that. You take a square, you fold like this, and then you fold like this, and then all boundaries are communicating. You wanna solve more examples, or we are done?
Want to know about salivary glands?
Oh, let's go then.
Yeah.
So you are modeling a cavity, okay? And the gland, the cells in the gland are your boundary, okay?
Okay.
And your field is an enzyme field. So the cells produce the enzyme, secrete into the vesicle and into the cavity, and you are modeling the cavity. The lattice is your cavity. The cells are the boundary. What is the boundary condition here?
Do you have your guess?
I think. Yeah. Constant value?
Yeah, constant positive value.
Yeah.
Good.
Okay.
Or because they are secreting, producing and secreting, regardless of the concentration of the enzyme in the cavity, they will keep secreting. So even if the concentration is the same, they will keep secreting.
Oh, so derivative.
Constant positive derivative.
Okay.
Oh.
I see. So there's just an outward flow.
Yeah,
Yeah.
there is a constant flow and always. So because your stomach is acid doesn't mean your I forgot the name will stop producing acid. So on and so forth. All right. Now the opposite. The cavity you're modeling, the cavity is the boundary, and the gland, the cells are your system. Same enzyme field.
Constant derivative negative.
Then what will happen when the cells have no enzymes?
I thought they would continue.
They will
to
go
produce.
negative.
But the cells continually secrete, right?
But yeah, okay, but you have a
Oh, you wanna
you
model.
have an enzyme field in your
Uh-huh.
in your system.
Uh-huh.
Okay, the cells are producing the fuel. How can I explain it?
Okay.
So
So there's
if you're constantly like pulling,
constant zero.
yes,
Okay.
it's like the corridor outside.
Yeah.
Okay, so why not constant derivative negative? The cells in the boundary with the cavity will go negative.
Okay.
They will go negative enzyme concentration. Does it make sense? Okay.
I feel
A
like-
small site of epithelial cells in the gland
Yeah.
where some of the cells secrete a specific, that's periodic.
Yeah.
All right.
So is that actually how the salivary gland is? There's just like this duct work and the cells just put out the saliva and it all goes out?
Yeah, that one?
Yeah.
Yes.
Ah.
There is many channels, like a channel system to maximize surface area, and they secrete and coming out of here. But they are all like a little bit different from each other. But it's the same principle. You maximize surface area with tubes, channels. There is one remarkable information. If you take all the inner membrane of mitochondria, the inner membrane of mitochondria is folded, right? Sometimes it's like if you sum up everything, it's like 20 times the plasma membrane, depending on the cell.
Wait, 20 times the membrane of the cell? Oh my God.
Yeah, it's a lot. We are a superpower. We're a superpower plant, actually, if you think about it.
Powerhouse of the cell.
Yeah. In CompuCell 3D, there are different diffusion solvers. In general, we will use the diffusion solver FE, that's the standard one. But there are other options. There are the reaction diffusion solver, where you can have multiple fields interacting with each other. That's not very common, but can do that. Let's say you are simulating a cell that is secreting an enzyme that breaks down a certain protein in the ECM. Then you may consider using reaction diffusion solver. There is the steady state one. It gives you the steady state right away. It's a little bit slower because it has to simulate until the steady state every Monte Carlo step. And for full documentation, see the manuals. Okay. To import the diffusion solver specs, codes, etc., you can, first option, import from the wizard. That's the standard one. In this case, you go to that page, in the simulation wizard, you type the name of the field, select the solver, click add. And that's, you can do this multiple times to add other fields. The other way of doing it is by going to the pull-down menu on Twedit++, CC3D-ML, Steppables, diffusion solver FB. Okay? Or the other ones. Some of them you'll see other, for example, kernel diffusion solver. Those are deprecated. In the XML, you'll find this piece of code. It is a Steppables called, and the name is the diffusion solver you chose. And the name of the field you put, diffusion field oxygen in this case. There is the global diffusion constant, global decay constant, they act everywhere, unless you specify the diffusion constant, a decay constant per cell type. So for example, here I have cell A, and cell A has a diffusion constant of 0.1, and the global is 0.12, so it doesn't make a difference, but it could be like 0. If I set a diffusion coefficient of 0 for cell A, then cell is acting as a barrier for the field.
So it's like you change like different values, different cells, but different like
Yes,
ways.
exactly. Epithelial cells are less permeable, so you can set a lower diffusion coefficient, so on and so forth. Okay. You can also specify secretion per cell. So if a cell is secreting, this acts like constant derivative positive, okay? Time derivative, a rate, constant rate. Okay. You also can specify the boundaries. There is a section called boundary conditions. You can choose periodic, constant derivative, constant value, all those we discussed. Okay. In the case of constant value, constant derivative, you always assign a value. Okay. Specify a value like 0, 1. You can specify an initial concentration. In this case here, I'm using a Gaussian exponential. It's a 2D Gaussian, so it's like a bell curve. And this is a quick demonstration. So if you specify the way I outline the slides, you will get this. So you start at the point with high concentration, it spreads out and fades. And the exercise for you is to generate a linear gradient. In such a way, it doesn't depend how you initialize the field. It will get to a linear configuration because you specified certain boundary conditions. So this is the exercise for you. So go ahead, open Twedit, start a new simulation. Yeah, go both of you there. So initiate a new simulation. You can put a cell or not, doesn't matter. And do the thing. And while I do the thing, I will get my 5 minutes break. And you do the thing.
Get
You were having you should notice, but you were having a 3 hours break with me. Ajay, I'm just going to drink water. My throat is sore. Oh, yes.
Which one did he say that we should use? Is it fast diffusion solver?
I thought it's
Diffusion solver and flexible? You can just go back on his.
yeah. Diffusion solver at the
Okay,
yeah.
I don't think you have to add any of those.
Oh.
Oh, I don't,
What do we need to do?
we need to set the boundary conditions.
Okay.
I think this is what's going. The boundary condition. Okay. So. We can change the diffusion constant and then the decay constants. Okay, then we can also edit the boundary conditions. So we wanted periodic Y boundary.
That doesn't matter.
Oh, okay.
This one is reasonable.
So
Cost there, isn't it?
Can you go back to the exercise slide? We had to change it to figure out which diffusion solver.
Yeah.
Diffusion over FE.
Yeah.
It's written here.
Right, but it was on the previous slide where it was describing the exercise, so that's why we went back.
Oh yeah, okay, no problem. Yeah.
But can we see that slide for the exercise again?
Huh? Ah, okay, yeah.
Okay,
Yeah, you need to change the boundary condition such that you achieve a linear gradient. How do you do that?
okay, so you just want. Wait. That could mean like a uniform concentration, or it could mean. The gradient between 2 points doesn't change. Even though it's not uniform, is that? Like what is the target here?
So you want to build a linear field, constant gradient,
So like linear decline in concentration,
or rise,
or,
whatever.
okay, but not uniform concentration,
No,
okay.
and your system, no matter the initial state, no matter the initial condition of the field, it reaches a linear configuration.
Yeah, so I don't actually understand the diffusion equation, I wanna see that, so. Do you remember, it's like, the diffusion constant times. I don't remember the terms.
Yeah, I just searched it out.
You don't need to solve the diffusion equation.
No, but do we need to remember what it is?
The diffusion constant. The diffusion constant, I will explain more with the interpretation, but it's how fast the spread out is. The spread is.
Oh, okay.
That's what it means. So if you set a higher.
Okay. So
Basically, we
higher,
reach the steady state faster.
okay, 0 would be no diffusion, right?
No diffusion.
And there's no maximum to the diffusion constant.
It gets lower. You can. I mean, you can put like 10. I would say is like enough. Otherwise, your simulation will get considerably slower because it calls multiple times to sort of keep up with the speed.
So here, under boundary conditions, when I open the XML, we've got this like plain tag. So we're, yeah, we have to set the parameter value. So we're setting the plain position. Like,
Yeah, plain mean, what does plain mean means? What does plain mean means?
the line of the boundary here.
Left, if you are talking about X,
Yeah.
X direction, or bottom if you're talking about Y direction.
Okay.
And if you're talking about max, the plane max
It's right.
is right
Or
in the
top.
X, up in the Y.
I see. Okay, yeah, that's. Just gonna start playing with stuff and see what happens.
I'll do that on my part here. Because I gave enough time, I think. So, new simulation. Doesn't matter. Doesn't matter. Chemical fields, oxygen, whatever. Doesn't matter. Which. Print out those. Here in the XML, this is the important stuff. Here I can set a larger diffusion constant just to reach the steady state faster. I'll give it a 0 decay because I want a linear gradient. If I give a decay, it will be exponential. If I set the decay, it's gonna be exponential. There's some secretion data, it's empty, okay, no problem. My version is different, so I have this constant value. Let's suppose I want to set a linear gradient across the X direction. I can set mean and max different constants like this. So let's say 10 to 0. And in the other direction, since I want a linear and nothing else, I choose a constant derivative 0, so there's no exchange in the Y direction. And now I run. It like it throws some random cells.
Yeah,
But okay,
so I had that problem.
that's not a problem. But it's gonna take a huge while, so let me go back here and reduce the size of the simulation to 40 by 40. Yeah. And let me comment this out, uniform initializer.
Oh, so if you have no initializer, that's how you get rid of the cells.
Yeah. I don't even understand how it builds cells, even though there's no cell defined,
Yeah.
but so eventually we get the famous gay pride flag.
Nope.
Let's,
Don't you choose that?
yeah, get rid of the cells. Mhm. Okay, and then, you would need to change that to constant value. Yeah, because right now it's constant derivative.
So what will happen if I set a constant value in one end and a constant derivative 0 in the other end? What will be the steady state?
Would the diffusion happen from one way to the other, then happen going back the other way? Once the concentration builds up on the other end and diffuses back out?
Yeah, until what?
Until there's just equalization? and
Yes,
okay.
perfect. And the equilibrium value would be the value of the field in one, in the end, you set the constant value.
So I think that, yeah, so you would want, maybe
Constant
it's that,
derivative?
the.
Oh, okay.
I think that's right.
Value, okay.
So try it again.
Makes sense. Yeah, this one won't work out the way you see there, because you set constant value 0 in the y planes.
Oh, okay.
And to reach like this type, you either want periodic boundaries on y
Oh, yeah, I did that.
or constant derivative 0. All right.
Oh,
And then last exercise,
Yeah.
oh,
Cause like the changes.
I finally got it.
and by the way, that's a way in the initial concentration expression you can reach steady state immediately. You can calculate what is the profile of the field from concentration in the left to concentration in the right, and set as the initial condition for your field. And that's how you reach steady state immediately if you want a linear gradient. So let me do that in my simulation. So here what I have this. And I'm going from 10 to 0, right? And it is diffusing until it reaches a linear configuration. Now let me go here in the initial concentration expression, and instead of x times y, I set it should be from 10 to 0. So it's 10 minus x, but x goes from 0 to 40, so I divide by 40. And that should be it. I think that's it. So I start, no.
Oh, yeah, I saw the equalization.
I did something wrong here.
This is kind of cool. So
Should go from
it diffuses, and then because this is
10
constant
to
derivative
0. Yeah.
it builds up there and diffuses back up.
Oh.
What did it do? Ah, of course. Yeah. Now, once I start, it's already on the steady state. Because the other way, so it's Monte Carlo step 0 there. You can't see it, but now it reaches the steady state immediately. By the way, I set up the expression.
You figure out how to pack into one time step all of the diffusion that would happen before it reaches the steady state?
Because I know what the steady state is.
Yeah.
I know the expression of the steady state. So if I input the expression as initial configuration, it will simply stay there.
Oh, I see.
Okay.
Okay, I don't really understand the details of what concentration expression means. I understand that it's a mathematical expression that somehow represents the concentration of the diffusant, but I don't understand the nuts and bolts.
It's the field. It's the field expression. It depends on x, y, and z. If you have 3 dimensions.
Oh, okay. But
So,
why
yeah.
is that only a function of x? Because it only varies with the x?
It is a function of y too, but here is independent of y.
Okay.
I could do this plus y. Look what happens.
Yeah.
Okay, yuck. Let's do something. Let's put a Gaussian here. Exponential. And here I think it's minus x squared. Yeah, minus y squared, let's say. Let's see. I think it worked. Yeah, I think it worked. If I set constant derivative there, we'll see the Gaussian down here. Yeah, look. And if I do x, for example, x minus 20, I'm centralizing into the middle of the lattice, right? If I do x minus 20, y minus 20, this Gaussian will start in the middle of the lattice.
I see, okay.
Right?
Yeah.
So I can start with a drop of a certain concentration. This is the expression is the field expression.
Yeah.
Okay. Initial condition.
Okay.
Yeah, so there are configurations to visualize the field. So if you go to tools, let me show you here. Tools configuration. In the field section, you can personalize a bunch of stuff. For example, the min max you can fix or put values to fix the color bar scale. You can also show contours, ISO values. If I press OK here, we'll see the ISO surfaces, these circles here.
Oh.
They are the ISO surfaces.
Yeah.
The representation. They work in 3D too, by the way.
And we had issues with that the first day, I think.
Yeah. And in the last few minutes, we have is interpreting diffusion constants. Let me see if I have. This is the last exercise, but I think we won't have time to cover it. And this exercise is basically placing cells in the middle with a different diffusion coefficient and plotting the concentration across the x-axis. And you see if you build this semi-permeable membrane, the steady state is broken like this in the picture, if it's semi-permeable. And then you can open a hole like this, and it's now a smooth transition. But it's still like kind of broken, like an inflection, because you have less diffusion from left to right because of the barrier. Okay.
So that's like the simulation we saw with the blue dots. The two vessels with the blue dots, where you were saying that the diffusion was caused only by probabilistic workings instead of collisions. Remember that slide? Like it's the same system basically.
Oh yeah, it's the same system. It's there and fast.
Sorry, that was like
It's there and fast.
my own brain can't use that.
Nice. I like it. I like it. Thanks. And the blue dots, it was like, what?
I'm sorry, yeah. The blue dots, you know those?
Anti-fusion.
Yeah, and there's a hole and they oh my god.
And about diffusion, what is important about diffusion? So I want to give you basic intuition about diffusion because I know it's kind of counterintuitive, diffusion. And it definitely doesn't behave like the stuff we see around. So diffusion, the diffusion coefficient is basically how fast things spread. So if you take a molecule, for example, a large protein, let's say a proteasome is a huge protein. Okay, a proteasome is a large protein that has to fit a full protein to degrade the cell, right?
Like it's a protein trash.
Yeah. It breaks down the proteins. The thrash just contains, right? It breaks down. So it's a huge protein. You expect that the proteasome to diffuse slower than oxygen because oxygen is super small, and oxygen is not an ion. It's not positive or negative. So you expect oxygen to diffuse faster than, for example, Ca2 plus.
Wait, is oxygen not an ion because it binds with itself? I can't remember the name.
Oxygen gas is O2 is not it's not charged. Okay. So for example, calcium 2 plus the ion calcium, it's gonna diffuse lower than oxygen, than water, right?
Because it's like there's a frictional force on it because other molecules grab it because of the charge.
Yes. So
Yeah,
it's called solvatation sphere, something like that. Solvatation. Solvation? No. Well, let's go with Portuguese. Solvatação. Solvatação de ions. So this is what I mean. If you take, for example, sodium, you have water molecules arranging around the charged molecules, and this increases the effective radius of the ion.
Oh, okay.
So it's gonna collide with more stuff.
Yeah, because it's bigger.
Yeah, and it's being dragged. Yeah, it's a huge set of interaction, but yeah. Another way of interpreting, and this is more mathematical, is that you can think of things spreading as imagining their distribution getting wider as time goes on.
But is the area under the curve maintained over time?
Yes,
Yeah.
because if you don't have like decay or secretion, insertion of more stuff, yes, it is. And fundamentally, this is called mass conservation, right? So you can think of diffusion as the width of this distribution growing in time, and it grows in a very specific way, which is the standard deviation squared grows with time. Okay, so it's not ballistic. It's not like growing. It's like growing like this and slowing down. Okay, because if you invert, it's the standard deviation goes in the square root of time. So as time goes on, it spreads slower and slower and slower. So James told me to put a slide where he discusses something called diffusion time, which is this. If it takes 3 seconds for a molecule to travel 1 micrometer, it will take 9 seconds to travel 2 micrometers, because it goes to the square root of time.
Yeah.
Oh.
Okay. I think personally that it leads to certain misconceptions about diffusion, because once it traveled 1 micrometer, it just has 1 micrometer left to travel. So why is not 3 again? And the answer is because it's not ballistic, it's probabilistic. So if you give it 3 seconds to travel, there is no guarantee to travel 1 micrometer. It could stay in place. It could go backwards. It could go anywhere else. So it's not guaranteed that it's gonna travel 1 micrometer. So although they will say, for example, oh, it takes about 30 seconds for this molecule to travel from one side of the membrane to the other, it doesn't actually work that way because it's probabilistic. But what you can say for sure is that you have an area where you expect to find your molecule with a, let's say, a 67% chance, which is the standard deviation. And it increases, this area where you can find the particle increases with the square root of time. That's the actual correct interpretation.
Is that what the Schrödinger equation is about? Or not?
It has something to do, yeah. Yeah, I don't know if it translates one-to-one, but so this is what this slide means by diffusion time and diffusion length. This is what I believe it's more correct. So the area where you expect to find that thing grows at the square root of time. And I have an example. So once my old advisor lost her dog, and she thought, oh, it's 10 dogs, 10 hours elapsed. Okay. So if it's a square root of time, I don't have to search in a much bigger place. Actually, it's proportional to the square root of time. So if you know more or less the speed of your dog, you can estimate the area where you can search for it. And this, of course, this is called the Langevin motion. And this is what justifies the diffusion behavior of proteins and other molecules inside a cell. What is going on? Huh?
That I thought that was coming.
What?
Random dog walk.
Random dog?
No, look what he wrote. Look what I put on.
What?
Go in the chat. Go in the chat.
In the chat?
You missed it. Yeah, see?
Random dog walk. Yeah.
We gotta make it fun.
Good. Yes. So, and if you solve the Langevin equation, and of course, I'm clicking the wrong computer. If you solve the Langevin equation, you see that the mean square displacement is this delta x squared over delta t is the diffusion constant. That's how it's defined. You solve the equation for the movement of this particle, and you derive the diffusion coefficient. And if you pass delta t to the other side, what you find again, that delta x squared goes with delta t. That's where this whole thing of diffusion time, diffusion length comes from. So the last thing would be to build this memory, but I think it's trivial. The one thing it's you will have to know here is that you can freeze cells in CompuCell. Okay, so to build this membrane, you have to freeze the cells, and you do that in.
Is it in the wizard?
You can do that on Wizard, or you can just do this. Freeze equals false.
Oh.
And it's free, it's frozen. So the cell will like stay there in place, it won't interact with anything. But you can set the diffusion coefficient, and the field will diffuse normally. So that's how you build that wall. So I think in the next class we'll come back with this exercise, or you can do it at home. It's easy enough, right? And then you can plot across the x-axis. If you want to do it and it's not easy enough, send me an email.
Okay.
And that's it. Let's go home. Oh, questions.
Yeah, maybe.